afternoon. This is CIVE633, Environmental Hydrology, Fall 2021. Today is October 14, 2021. And the objective of this class is to explain or solve the problems of the midterm, which took place 2 days ago on October 12th. The exam is structured in 12 questions, 12 essay questions, of which the students are supposed to answer 10 for 100 points. So I'm going to go over the questions, first state the questions, and then proceed to discuss or explain what would my answer would have been since I posed the questions, okay? So let's get going here. The first question relates to environmental hydrology, the influence of the four fundamental sciences as they are geology, geomorphology, hydrology, and ecology on the environment in a different system. And for that example, we have the Pantanal of Mato Grosso, in which I worked for, I don't know, almost 20 years in the late 70s to late 90s. So the question is, what is the most important hydraulic parameter in the analysis of the environmental impact project of the Pantanal of Mato Grosso? This was a waterway project. In other words, had to deal with management and modification of a river. The river was the Upper Paraguay. The answer in this question is the slope. The slope is the most important parameter. Actually, the slope is a very important parameter in hydrology and hydraulics, but in this case is the most important. That's basically the correct answer. And why? Because it controls the flow. And I'm going to give you something or talk about something that perhaps I did not mention. I think I did actually, but I didn't explicitly talk about it. When we did the study on the Pantanal, we were surprised by the low slope. The slope was 0.00001, which is 1 centimeter per kilometer. And I was really surprised that it was that low. And I asked myself, well, that's weird, because you don't find around the world that many cases. So then I said, well, what about downstream? So I took the time to continue to plot the slope downstream, because I figured there was something in there that was hiding, that was in hiding. And downstream is the middle Paraguay and the lower Paraguay, and then comes the Paraná. That's the way it works. And the Paraná drops or deposits the waters in the Atlantic Ocean at Buenos Aires. Okay, so it turned out that the middle Paraguay and the lower Paraguay had normal slopes. So how do you have a situation where you have a very low slope upstream and then normal slopes in the middle? It's the opposite of what it should be. Most rivers have high slopes upstream and low slopes in the middle. This one was the opposite. And the reason was that there was a hump. There was a huge hump. So we looked at the geomorphology. At that point, we say, well, this is all controlled by the geomorphology. So we looked at the geomorphology, and it turned out that tectonism, that is mountain lifting in general, has raised the lower part of the upper Paraguay at around the place where the Paraguay ends, which is called Puerto Murtinho, 40 meters over the last, I don't know, anybody's guess, geologists guess, I would guess 5-10 million years or more, even 100 million years. It has raised to 40 meters. So in the act of doing that uplift, it has created the Pantanal, because the Pantanal wasn't really supposed to be there. And it is there only because the uplift. That we understood. that's the major uplift, like the central. But there's other situations of uplift along the upper Paraguay, which make its slope not a convex slope. I'm sorry, not looking at it from above, it makes it um, convex, meaning there's humps. That is the issue. So the slope is the issue because of the tectonism. I think I can stop there. But I had discussed this in class, and I said that if you mess with the slope, you're changing the Pantanal. If you blow the rock outcrops, you're changing the Pantanal. It's like those rock outcrops are little dams. Well, not that little, but they're dams. And if you blow the dam, the water runs off. That's it. So that's the answer to that first question. On the second question, describe the four geographic characteristics hazards posing a high risk of contamination of groundwater in the case of the Campo Regional Landfill project. We did a study of this in the year 2010. There was a company that had done, I don't want to mention names, there was a company that had done the environmental impact study. Those typically are reports that have 2,000, 3,000, sometimes even more pages. They cover just about everything. That's the way they do it. Okay, they hire somebody that is used to doing these things, and they produce this huge volume that many times people cannot or will not read. Um, so then they had a review of it, and I was hired by East County people to do a rebuttal. No, not a rebuttal, but comments. They wanted, there was a 3-month comment period. And that's very common in the environmental laws of this country. So I did a comment, and the comment was supposed to be critical, right? So we basically, because I was being hired by the people that were opposing the project. That's good. The good thing to understand. Engineer then becomes a lawyer. Only that he's a lawyer that possesses knowledge, which is technical. Okay, so we wrote this report or studied the situation. And by the way, that was not the first time I had worked there. I worked on, starting in the year 2005. I worked on the region Boulevard, the Boulevard region of East San Diego County, which is in the corner southeast corner of the county. The county abuts with Mexico, right? In the southeast corner, um, Campo is very close to it, but Boulevard is also very much south. As a matter of fact, the Campo Regional Landfill was being proposed right at the border because that land belonged to the Campo Reservation, the Campo Band of, I believe it's Campo Band of Mission Indians, the full name. So, so I was told to do this and given some time and some resources. So I think it was 3 months and some resources. Actually, the report was done in 1 month after we did the study and read all the reports and stuff. So we identified four hazards. Basically, we were going to say you shouldn't do this project because, okay, and the because had to be very strongly worded technically, of course. So we did that, and we came up. The number one cause was that they were doing this. Um, they were doing this. They were going to put this landfill on top of a hill, and in proximity to the groundwater. The groundwater was right there. We proved that. You have a video to show that, by the way. We have a video from 1993, which is the El Nino year. Rained a whole lot, and the entire groundwater level in the entire region of Tierra del Sol, which is where the Campo landfill is located, raised to the surface and even became artesian There was so much pressure, there's so much water that the water was popping up, a couple feet off the ground. So that is really amazing. It really is amazing. So the fact that it was on the groundwater level. The second point was that it was an aquifer. It's a rock aquifer. Rock aquifers are not alluvial aquifers. The alluvial aquifers works diffusively, while the rock aquifer works convectively. If you guys, those of you that are taking computational hydrology with me know the meaning of convection versus diffusion. Convection is a first order process. Diffusion is second order. So where convection exists, diffusion takes a second place. If convection doesn't exist, diffusion is all there is, so it has to be first place, right? So, um, so the third item that we raised was that it so happens that Campo, the Campo Valley, which is located a few miles from the place, holds the record of the largest or most intense precipitation in the state of California, which happened in 1891. They recorded 11 inches in 100 minutes. 11 inches in 100 minutes is a lot of rain. So then we argued, I think quite correctly, that you were going to have a lot of water. It's going to start washing things out. Okay, and then fourth one, region. That region is an earthquake region, and we were lucky again that a month or a few weeks before we released the report, the region had its strongest earthquake in many years. And so there were errors in the report, small errors that we picked on. But the point is that we wrote the report and there was some decisions made. But to my understanding, I'm pretty sure the landfill was canceled. It was never built. I don't know what they're going to do. They're going to move somewhere else. I mean, I'm not privy to that information. I'm not in their activity. I mean, I'm talking about the Campo Band of Mission Indians. But that was the end of that project. So I listed them already. So now we go to number 3. What 5 properties make water a suitable medium for life? Describe in detail. Okay, that is part of a report that we put together. The first one is the control of temperature, control of ambient temperature. Water is very much known for that. The second one is, I'm taking a look at this, it's the floatability. I'm trying to remind myself of these items as we describe because we got to continue. The second one is a floatability, the floatability. When water, allows the ice to float and permits the survival of biota in the ocean and in the lakes, also the lakes that are north enough so that they could freeze. The surface tension allows the plants, the capillarity related to surface tension, and allows the plants to pump the water. The water reaches to the plant and then the plant to the roots, and the plants then pump the water. That's important for vegetation. And we know that a lot of the water, I wouldn't say a lot, most of the water that comes into the deserts is coming from the groundwater. As a desert, it doesn't rain enough. If it didn't have the groundwater, if the desert didn't have the groundwater, it will die. But thank God it has the groundwater and it's close to the surface. That's what it's called in normal terms. It's called an oasis. The oasis flourishes because of the groundwater. It's not flourishing because of the surface water or the rain. It's marked solvent property, for sure. Water will dissolve almost anything. That has been demonstrated. And the fifth one is active relation with proton and electron chemistry, which as you guys know, it leads to many other relationships of pH and PE that we're going to come back to discuss later on today. So, number 4, describe the 5 processes that form part of the nitrogen cycle. Those were explained in both the Fish and Wildlife Service report in Oregon, as well as in our report and video on the Janos de Mojos in Beni in Bolivia. The first one is nitrogen fixation. Without nitrogen fixation, the process of biota creation, I guess development, will be slower, will be much slower, because the plants need nitrogen. And if nitrogen is either not contained or exhausted in the ground, they're not going to be able to grow, because nitrogen is an important. Remember NCHOPS. Remember the acronym NCHOPS. Nitrogen, CHO is the matrix, the body. CHO is carbon, hydrogen, oxygen. So NCHOPS is nitrogen, phosphorus, and sulfur, the other 3 major components of the biosphere, as a matter of fact. So the 5 processes. The first one, nitrogen fixation. The other one, ammonification, the conversion into ammonia, the production of ammonia, which is needed. Ammonia is a gas. Then after that comes nitrification. And nitrification has 2 steps. The conversion of ammonia, which is a gas, into a solid, which is nitrogen dioxide. No, I'm sorry, nitrite oxide. And then that in itself is converted still by bacteria to nitrates, to NO3, the NO3 radical. So you have in there ammonification, nitrification. Then denitrification. The end product of the recycling of the whole thing is denitrification. And the denitrification allow the denitrifying bacteria allow the nitrogen to return to the atmosphere, fulfilling the cycle. And then there's one more, assimilation into organic matter, because the plants need the nitrogen. So those are the 5. What natural process is question number 5? What natural process is responsible for the oxygen present in the atmosphere? Photosynthesis. That's simple. That's just a question of photosynthesis. In what process is responsible for the nitrogen? We believe it's denitrification. There was some denitrification in there. It's hard to believe that all that nitrogen in the atmosphere came from the volcanoes. I mean, I wasn't there, so I can't really for sure tell you. But I know that denitrification, in the past, the world had a lot of water, perhaps much more water than we have now, surface, a lot of wetlands, and the wetlands denitrify because the oxygen doesn't diffuse as quickly as in the air. And when they denitrify, they become anaerobic, and therefore it lends itself to denitrification. So what process is responsible for nitrogen? The denitrification. We do not know, and this has not been written. There's a book on denitrification that I have read, but I think the general sense is that denitrification had something to do with it. And now we realize, of course, that the amount of nitrogen is 4/5 of the atmosphere. And I think I said in class, maybe I said it, maybe I didn't, that we are alive because of the nitrogen, not because of the oxygen. We need the oxygen to burn our food. And everybody looks at the nitrogen, you got to burn your food with the oxygen. Without oxygen, you can't live. But we fail to realize that if we breathe oxygen, we will burn. So the nitrogen is an inert gas, and it allows for the system or the process to continue without the suspect, ourselves, right, burning up because of too much oxygen. I don't need to tell you. You know that if you go to the hospital and they give you too much oxygen, they could kill you. Okay, it's got to be under highly controlled conditions. Explain the concept, number six, question number six. Explain the concept of a 800 millimeter of the 800 millimeter isohyet. We're doing well in here with time. How does it promote sustainability? Okay, I think I told you the story. It bears repeating. It's a nice story that I had toyed around with these concepts for 20 years, and I thought that they were known. And I had a meeting, a visit with an architect one day, and I mentioned, I said, the 800 millimeters, like if it were something everybody knew. And he says, what's that concept? That's an interesting concept. Give me a reference. Where'd you find it? I said, I don't have a reference. I don't have a reference for it. So then I decided to, no, there's no reference. So I decided to come up with a reference. I sat down, even that night, I think, and within the next few days, I produced that paper that I have had you read, the 800 millimeter isohyet, Health and Hope. Now, how is it that I wrote that paper on health and hope? It looks like something like I'm a psychologist or a physician, but we tied it in nicely. And let me tell you why. As we explained in that paper, there's two components, there are four components. There's the sun. There's nothing you could do with the sun. You can't move the sun. You can put some clouds in there. Actually, you don't put the clouds, but the clouds can come in and hide the sun for a while. But the sun is there. Okay, so you can't change the sun. But there's nutrients and there's water. And we know that the ecosystems in general, the biosphere, is about 95 to 98% water. The figures vary. I don't know why, but it must be, depends on the species, right? 95 to 98%. In the rest of nutrients, a variety of nutrients, at least 20, if not 40. The trace elements, or the trace, that's right, the trace elements, like the, the salts and all others, aluminum, iron, molybdenum, and all sorts of others, which I have listed. Actually, I took that list out of the Scientific American series of papers of 1970, which are an excellent source for this kind of knowledge. So, but in reality, I have seen in other references, there's up to 40. So 40 out of the elements of the 120, 130, I don't know how many at this point, elements in nature, about a third of them are needed by the biosphere. And that's what we think. I mean, nobody knows everything, right? So then, since I worked on deserts and I worked on humid regions, I worked all over the climatic spectrum. I was in India in a very wet region. I've been places in Brazil, northern Brazil, extremely dry regions. In Brazil, they have 8 types of plants, and they vary in terms of their moisture needs. 8, all the way from the Seridó to the Mata, going through various Portuguese names. But so that's a laboratory. I was there in 1993. That is a laboratory for study the relationship between water and vegetation. And I said that in a paper, but I'm getting outside of the topic here. So we needed, I understood that there was water and nutrients. I also knew that water was available in large quantities in the Amazon or in the tropical rainforests, and that nutrients were available in large quantities in the desert because of leaching, the leaching process. What is the leaching process? The leaching process is the leaching of the nutrients from the ground by rain. If it rains a whole lot, the ground has no nutrients. That happens in the Amazon. On the other hand, if it doesn't rain and the ground is relatively geologically new, it will have a lot of nutrients, like packed like a chocolate bar. It's good, but then you got to throw in the package. You can use the good nutrients, but you have to throw in the package, just like a chocolate bar. Okay? So then the question was, if at 100 millimeters, you have a lot of nutrients and no water, 100 millimeters of rainfall per year, which is arid or super arid, you have, at that point, you have a lot of nutrients but no water. And then you run on to the other side of the climatic spectrum, or the precipitation climatic spectrum, um, to 2000 or 3000. The Amazon is 2400, 30, 20, how did I say? No, 3200. The central eye of the Amazon, which is in northern Brazil, is about 3200 millimeters. We knew that. And therefore, we can surmise, I mean, that's a mathematical theory of the maximum. You know, if two things are converging toward the middle, then the middle is going to have the opportunity to have both of them, not in an extensive amount, but maybe in the right amount. So that's where we developed this concept of the 800 millimeter ISO Hyatt, because we visited a lot of places. So the only thing I had to do was to figure out it was going to be 1,000, or is it going to be 900, or going to be 800. And at that point, I said, well, it really doesn't matter. Choose, pick one, and that's it, because it's going to be almost impossible to prove you wrong, right? Because I mean, a person would have to do a complete measurement throughout the world, and that's impossible. So we're going to go here with a little bit of feeling of what the value it should be. I did a calculation based on the work of the Russians have done. The Russian scientists have done in their famous publication World Water Balance, 1978, and came up with the number 825 in one of my papers, hydrology papers. I know Livovich had done work in this area, and he was coming up with 900. And I know other people, the geographers, were coming up with 1,000. So I chose 800. Why did I choose 800? Because I thought it was a Kabbalistic number. 2 squared 4, the cubic of 2, and 2 is a very basic number. So we figured 800 millimeter would do well. Now that doesn't mean that 900 is not going to work. 900 will work too, because it's close to 800, right? So that's the way. Besides, this allowed us to divide the climatic spectrum in from 800 to 400, from 400 to 200, and 200 to 100, and then go beyond it from 800 to 1600, from 1600 to 3200, from 3200 to 6400, and from 6400 to 12,800, which matched all the experiences. All the experiences. We have an experience of Cherrapunji in Assam, in India, where it rains 12,200 millimeters per year. That was at the end, at the extreme end of the climatic precipitation spectrum. We also have the experience of places where it rains 50 millimeters, which is nothing. As a matter of fact, I was born in Lima, Peru. And in Lima, Peru, if it rains, it's a miracle. It's 30 to 50 millimeters per year. It's a desert, complete desert. The Peruvian deserts are some of the driest in the world. Okay, so that is the concept. The 800 millimeter ISO high would have a balance of nutrients and water. How does it promote sustainability? Well, if you're in a rainforest and you were out there by yourself, you could not sustain yourself, because you'll be forced to eating just nuts, and some very few products can be grown in the rainforest. You can't grow corn. You cannot grow potatoes. You cannot grow other things that are basic to our usual food that we eat. So that's so it lacks the right hand side, the wet areas are lacking that. Now on the left side, in the deserts, okay, let me just go over here. In the deserts, you have a lot of nutrients, but you don't have any water. You got to bring the water. You got to make an effort to bring the water. And that effort, you could pump the water like we do here in California. We get the water from the north. It rains a whole lot in the north. We pump it and we bring it over here. Interestingly enough, the geomorphology is not helping us because you can't use gravity, so you got to pump it. We pump tremendous amounts of water from the north, and unfortunately, we're doing that with fossil fuels. So eventually, nature comes back to for her payment. You know, now the fossil fuels are going to change the weather, right? So there's a problem. There's a problem there. There's a problem on the other side. So the problems, my contention is that the problems are minimized at the 800 millimeter isohyet. Mexico City sits at 800 millimeter isohyet. It has 24 million people. I'm not advocating that you get together 24 million people, but I'm telling you there's something in there that is making sense, right? In a broad range, because nowadays we have subsidies. Subsidies is a word that says we're being helped. We're being helped by whom? By the industry. The industry is moving things around the world, as a matter of fact, and allowing us to be kind of together. But the transport, and we should realize this, that the transport, particularly with fossil fuels, is expensive. Hopefully, in the future, we're gonna separate ourselves from the fossil fuels, and it will become back to the way it was 200 years ago. But we need to find a way of energizing the transport, and we're doing that, but it will take some time for us to get there. So how does it promote sustainability? That you don't have to work hard. You don't have to work hard and use subsidies because it's right there. That's how it promotes sustainability. So that is the answer to that question. Question number 7. Have humans solved the problem of handling their own wastes? This is interesting. Most of you said no, and there's a couple that said yes. And I was going to take both answers correct because we are here to show things, to show how things are explainable today in science and society. Okay, and the systems that we currently have right now, I was surprised to hear that when I asked Google about what percentage in the world had the system that we have, which is called toilet and drainage, transport and cleaning, that's about 40–50% of the world. There's a 50% of the world that does something else. I was curious to find what they do. Well, they have 3 or 4 systems that they have. They may not be as clean because they don't separate yourself from the stuff. You know, the cleaner you are, is the more separated you're from the stuff, from your own wastes, right? They may not separate the cleaning, but they do a better job in terms of sustainability. Sustainability, because they're not using the energy particularly the fossil energy that is required. And I have an example for that, which I think I shared with you in class. I was in Illinois at my brother's ranch, and I asked him. I said, "I know you live on this hill, and you got this. I mean, the system works well. Where do you hide it?" And he says, "Well, I wasn't going to talk to you about it, but now that you mention it, let me show it to you." And he says, we went out in the field, and he says, "Over in the corner, that's the corner of my property. The septic tank is there." So you see, so that's the way he solved, because he was living in a rural environment. So that's the way he solved his own waste. Like him, there's many other people. Like I said, there's various ways. So the answer to that is no. If you really believe deeply in your heart that everything we do has to be recyclable. Yes, if you believe that we've done a great job in the last couple hundred years, but we still have some to do. That's basically the answer. We have some to do. San Diego is throwing into the ocean 50% of their runoff of their sewage. 50%. Yes, that they can't. It's too expensive to treat. I believe they do advanced primary. I could be wrong on this, but advanced primary. So that means 50%. right about 50%. Okay. Why I'm going 610? So we're fine. We're fine. The eighth question, the question number 8 is, why is it a fallacy to state that tropical rainforests such as the Amazon will help in sequestering carbon from fossil fuel burning? It's been said by society in various forums that it is of our interest, meaning the developed world, to hold on and preserve the rainforest. And the Amazon rainforest is the largest rainforest in the world. The idea is that the carbon dioxide is going to go into the rainforest. As a matter of fact, there's data or arguments, I think it's data published by the Scientific American suite of papers back in 1970 that says that of all the um, carbon dioxide that is being pumped by fossil fuels into the air, about a third is being absorbed by the vegetation, which is kind of good. Another third is being absorbed by the ocean, which is kind of bad. And then the other third is what we see. So if it were not for the vegetation and for the ocean, we would be in bad shape at this point. After 50 years of earnest developed, or rather coming up with all this stuff, it's been only in the last 50 years. Well, I mean, it does vary with the curve. The carbon dioxide concentration has grown up about 30% in the last 50 years, 60 years. Um, that's been demonstrated. So, but if you study the ecosystem in the Amazon as Welch has done, which Welch is a professor of environmental engineering over at University of Oregon, I believe, or it could be Oregon State. No, it's University of Oregon, Seattle, right? Seattle. That he has studied this, and we in conjunction with all the other ecologists, and they do realize that there are climax ecosystems. A climax ecosystem like the Amazon is in balance. In other words, the amount of photosynthesis, which occurs every day, is balanced by the amount of respiration. Now, there's not a whole lot of people in the Amazon. The Amazon has a very low density of population. So who is breathing out there? There was breeding of the bugs in the ocean, in the Amazon, but I believe that the major component of the breeding is the breeding of there's a lot of bugs and a lot of animals, a lot of wildlife in the Amazon, and they're all breeding. So the argument, and it's a good argument, is posed by Welch, that there's a balance out there, or near balance. So you cannot store carbon in the Amazon. The Amazon has an amount of carbon and it's going to stay with it. Interestingly, though, research has shown that the Amazon is such a strong climax ecosystem that it is expanding at the rate of, I read it in one reference, at the rate of 70 meters per year. What does that mean? The Amazon is big. It wasn't born yesterday, like millions of years. And it keeps growing at the rate of 70 meters per year. Every year multiplies 70 meters by the perimeter. And that's the growth of the Amazon. Yep, that's it. So it is a fallacy to state that the Amazon is going to take the carbon. The Amazon doesn't take hardly any carbon. Number 9, explain the concept of DO-SAG curve. How does the Ponce DO-SAG curve equation differ from the Streeter-Phelps equation? Okay. Rivers have dissolved oxygen. Like we have oxygen, 21% in the atmosphere, which we breathe from the 21%. In the water, particularly the rivers, the ocean too. I mean, the lakes too. There's got to be dissolved oxygen for the fish in there. If the dissolved oxygen disappears, the fish will die. The fish have to breathe also through their system. They breathe also. The fish need the oxygen much as we do need the oxygen. And the problem is that the oxygen in the atmosphere, there's a lot of it, 21%, and it's easy to reach. I mean, I can just go outside and breathe. I can breathe here. The oxygen diffuses everywhere. But the diffusion of oxygen in water is a lot slower. So if you start getting the oxygen out or taking out the oxygen, it will not replenish as quickly. Okay? So what happens is that in the past, the oxygen in a body of water has a tendency to reach saturation. So it should be at saturation or close to saturation under normal conditions of nature. Okay, so the saturation level for DO in water is about 8 to 9 milligrams per liter, or ppm is the same, milligrams per liter. So what happens is that we started dumping sewage in the rivers, we society. And we started doing that about 120 years ago, plus minus 20 years. That depends on where also. If you were in England, you were doing it earlier because the English developed this system back in the year, I think 1870 or 1880, something like that. They developed the system we use. Then we all took it because it appeared to be at the time a good system because we had not seen the effects. Okay, so when we dump sewage, the sewage is food for the bugs, thank God. So we actually create an artificial ecosystem where the bugs of the microbes are flourishing because they got new food, right? Imagine if you were poor and somebody dumped food, then you decided, oh, I'm going to have a larger family because this is easy, right? So then the bugs start growing on the food that we gave them, the sewage, and then they take all the oxygen out very quickly. And therefore, they die without knowing, of course. They don't know. They die. And that's exactly the way it happens. So there's a drop in the DO, which follows an exponential law. It starts at 9, 8, 7, 6, 5, 4, and by the time it gets to 0, the system becomes anoxic. There's no oxygen, free oxygen in the water, and then all the bugs that need oxygen die, and then the anaerobic bugs that are somehow hiding in the ground in the strata, they come out, they flourish. It is well known also, by the way, I keep mentioning the Scientific American, that the metabolism of the anaerobes is about 10 times slower than those of the aerobes. Therefore, they cannot do a whole lot, but they do. They still do. That also is coupled with the fact that it contributes, or rather causes, the development of hydrogen sulfide, and that substance, you know very well, smells of rotten eggs and other very noxious odors. So when a river goes bad because of excess sewage dumping on it or in it, it starts to smell. I've been around the world and I've seen many places where all the rivers smell, including in Mexico. I was in Spain once and I saw it. In the United States, to be honest with you, I don't know. There may be some, but we have very strict regulation here in the United States, laws and regulation. And therefore, people are afraid of missing it because they will be regulated. The laws will be applied to them. In other places, I'm afraid to tell you this, but the laws are there, but regulations not. Like in Brazil, it's like that. One Brazilian told me like that, oh, we got all the laws. We copy the laws, we have all the laws. We don't have regulation, therefore we don't have enforcement. People still do it because they know that they can get away with it. Now, I'm not advocating that all countries in the world get into the regulation. No, I'm just telling you those are the facts. Those are the facts. Um, there is not means or willingness out there to do the regulation that is required in order to make everybody comply. However, nature is helping us because nature comes in and says, "Oh, this thing is got to replenish." Even if these people who would dump the sewage are not there, if something happens as a weird situation, you know, some some natural trash was thrown into the river by accident or something, and it's going to have to replenish. So she created the process of replenishment. So the water eventually will replenish to the point where it should be, which is 8 to 9 millimeters, not millimeters, milligrams per liter. So what happens is a process of it's a duality. One system or one process, physical chemical process or biophysical chemical process, trying to draw the DO curve down, and another one trying to raise it. So somewhere in the middle, you'll find a situation where, depending on the conditions, you can reach a bottom. You reach a bottom, and then it starts coming up. Eventually, reach a bottom and starts coming up. If you get enough time and/or space, it will come back. If you dump sewage in an ocean and stop the dumping of the sewage, within a few, I don't know, I can't tell you that, but it has to be calculated. Within a few, some time later, it cleans itself up. Okay, so so that is the DO-SAG curve. How does Ponce DO-SAG curve differ from Streeter-Phelps? When I was doing this work, I looked at Streeter-Phelps. Streeter-Phelps is a 1926 equation. And I think I mentioned to you in class that you would recall that I said that Streeter and Phelps could not have used computers because they were working in 1925. Okay, computers became widely available in the United States in the year 1955 and 60. Okay, so imagine we've been what 60 years and we've had computers. Can you believe it? Those of you that are young will not even start to believe what I just said. That 60 years ago we had nothing of what we have right now. So, but I'm most of you that know me know that I am a numerical guy. A numerical guy means use the computer to do calculations. So then I decided that I was going to solve the Streeter-Phelps. I got the Streeter-Phelps. I'm going to solve it, but I'm going to solve it numerically. I'm not going to solve it like Streeter did analytically. And you know, there's an analytic solution for anything in a numeric solution. The numeric solution has a methodology, and the analytic solution also has a methodology. So you can compare apples and apples and apples and oranges, but the point is that actually they're apples and oranges because they have a tendency to be different. So the methodology the Streeter-Phelps used, I looked at it, but I didn't think it was worth my time to get into it because I accepted what they said. And in fact, that equation has been used for design for more than 1926, almost 100 years now. So then I said, I'm going to do the numeric solution. We did the numeric solution. And lo and behold, in our numeric solution, the isolation point or instability that that equation has did not show up. Because if you know the Streeter-Phelps, the two coefficients that control the computation, one of them explains the decay or is the rate of decay, and the other one is the rate of growth. The equations are not the same. The growth is almost linear. The decay is exponential. But you got to find somewhere in the middle. And for whatever reason, I can't tell you exactly why, these two coefficients were coming up as a subtraction in the denominator of the front of the equation. That means that if these two coefficients were equal, the equation, the Streeter-Phelps equation was going to blow up in its solution. Anybody that knows algebra would know that. Therefore, the Streeter-Phelps is undefined for when these two coefficients are equal. Now, the question, of course, is when are they equal? And the answer is probably not in many few cases. One of them is about 0.3 and the other one is about 0.6 or 0.7. But they have variability, so that could be the case. At any rate, we figured that we had come up with a more modern solution to the times, right? This is not 1926, which had no limitation as far as what values are. We ran the computer with both methods, and sure enough, if you said case of O and case of C, I think those are the names, equal, the street felt blew up. Locally, it blew up. While our equation did not. So how does the Ponce differ? Our equation doesn't blow up when the K's are equal. How did the early inhabitants of the number 10, by the way, I forget to mention the numbers. How did the early inhabitants of the Janos de Mojos manage to open the nitrogen cycle? How harvesting tied to how is harvesting? Let me expand this a little bit. How is crop harvesting tied to the opening of the nitrogen cycle? Okay. Now, in 1993, I had an invitation by a professor, I believe his name is Professor Erickson, professor of biology, um, I think it was Penn State. He invited me to go out there to the Llanos de Mojos. I'd never been there. It's in the Beni, in eastern Bolivia, because he said that there was he's an archaeologist, or he was, I don't know, I haven't talked to him in 30 years, but he was in the Llanos de Mojos because he was there to study the work that Denitrification, uh, American geographer, had uncovered in the year 19, it was in the year 1964, 65, the book by Denitrification, which is called the Aboriginal Cultural Geography of the Llanos de Mojos. So Erickson was there to study it, and he wanted to get some pointers on the water part because he's an archaeologist. He's not a water guy. He's not a hydrology guy. So he asked me to go out there and visit with him, and of course I promptly accepted. I love projects in the field and stuff. So I was there for about a week, and we took a look at the system, and I learned about the Llanos de Mojos. I took pictures, and people were saying in the literature that these were, of course, anthropogenic. That had to be anthropogenic. There is no way about it. And the reason why is because they all have different shapes, like 3 or 4 or 5 different shapes depending on the location. If you have in nature, she would have done the same shape because if it's eolic, wind generated, then you'll have some kind of process underlying it. But no, in this case, totally different. But they were all earth mounds or hummocks, elevations in the terrain, which is not the whole terrain, just strips of elevation with raised about 5 feet. Because I was standing, and when I have a picture of one of those, I have a few pictures. So I got to find them. But the point is that the inhabitants of the Llanos de Mojos in pre-Hispanic times built these hammocks. When? My guess would be that between the year 1000 and 1500. 1500 is when the Spanish arrived. Or perhaps they're even longer. I'm not the archaeologist, and I haven't talked about the age of these mounds, but they're there. They're there. So the inhabitants of the Llanos de Mojos managed to open the nitrogen cycle that way. Well, they provided periods, in the mound, you have periods of aerobiosis and anaerobiosis. While if there were no mound, it will be all, it will eventually close the nitrogen cycle, denitrify, and lose all their nitrogen. In this way, they avoided the strips on top of the mounds of losing the nitrogen. That's what happened. Now, I realized this, and I eventually decided to write it up because I thought it was correct. And I have enough experience in those types of ecosystems to realize that that is in fact the case. The Pantanal of Mato Grosso has a lot of earth mounds, natural earth mounds, not human built. And there's a lot of vegetation that would adapted to the earth mounds, not adapted to the grassland. There's a lot of grassland in the Pantanal, but the grassland cannot be used for exporting crops because there's no nitrogen in the very little nitrogen in the grasslands. Well, the mounds have nitrogen, but the mounds in area-wise amounts to not too much. So business in the Pantanal of Mato Grosso, as well as in other areas, similar areas around the world, concentrated on the raising of cattle. Of cattle. The Pantanal, with the last time I saw the figure, had about 10 million heads of cattle. One day I was there in 1995. I visited because I had another project over there. I had 2 or 3 projects in the Pantanal, and traffic was interrupted on the main road for about an hour. And I said, well, you know what's going to happen? Well, we have to have the herd go from left to right. We're taking the herd somewhere else. And you have to, by the way. If you're a good cowboy, you know how to take your herd here and there, right? Because they got to eat. A cow, only thing it does is eat every day. If you looked at it, if you looked at them, that's all they do. Besides, the owners also want them to eat every day because that's what they do. They want to sell the cow later, right? So, in the Pantanal, the industry is kind of raising. The mounds are not used for anything. The mounds are used for wildlife, but that's not very productive in terms of the economy. Okay, so how is crop harvesting tied to the opening of the nitrogen cycle? Right, you have to have an open nitrogen cycle in order to do crop harvesting, and that was done by the early inhabitants of the Janos de Mojos. Now, did they know physics? Did they know chemistry? They knew water hydrology? No, of course they didn't. They just did it by gut feeling. Or some person out there saw it, experienced it. They're not dumb. They're just uneducated like we are. Okay. So they figured they could do it. And they started propagating the idea that they could do the earth mounds. And by the way, this issue of the earth mounds is not just Brazil, it's not just Bolivia. It's in many other parts of the world. I am given to understand that that's the case. It's not localized to these 2 countries in South America. Explain the concept of redox potential. So what is redox potential? Well, I have it I'm going to read it for you from our paper. Redox potential is a measure of the affinity of a substance to lose or gain electrons and thereby to be oxidized or reduced. And we have a very nice picture that I pulled out of a book which shows that when you reduce, you gain an electron. And when you oxidize, you lose the electron. Now, what are these electrons? Electrons are parts of matter, parts of nature. The only problem is they technically don't have any mass. Well, they do have, but it's so small compared to the actual nuclei or nucleus that they consider not to be, I'm not going to say it's not important. They just take second place to the protons, right? So the protons is what we eat, we digest, and so forth, all the elements, protons and neutrons. But the electrons are always there. There's clouds of electrons. As a matter of fact, electricity, I don't know too much about it, so I'm not going to talk about it, is formed with the electrons. So, so the electrons are there. And we know now that the concept of redox potential is related to the transfer of electrons. So oxidation vis-a-vis reduction. When you take out the oxygen, then you reduce. If you add oxygen, you oxidate. That's what it is. So it's called redox. Interestingly, though, the concept leads to, in some quarters, in some places, it leads to the concept of PE, which is kind of parallel to that of pH. Everybody knows pH is the percentage of hydrogen, nuclei or protons. Okay, but the name PE is not very well known. There are some few places that mention it. Most people talk about the redox potential. So that is what redox potential is. It's really a way of saying PE, percentage of electrons. I don't like to create another word, but I've seen it. I've seen it in various places. So that's the concept of redox potential, fundamental in the issue of wetlands. I came up, I'm not a microbiologist or a biophysicist, so I came up, I'm a civil engineer, and I came up with this concept about 20, 25 years ago because I was studying wetlands and I had to do it. I had to learn all this process and as part of my environmental education to be able to teach this class. So that's redox potential. What's methanogenesis? Well, in the science of wetlands or wetland science, there's a book by Kadlec. Professor Kadlec has a very thick book. It's about 3 or 4 inches thick, about 1,200 pages, where he shows this little graph, which is it's just a graph that shows the processes in wetlands, beginning with oxidation, normal oxidation, burning of oxygen, and then once the bugs, because it's the bugs, not us, we're not there in the wetland. The bugs are the microbia are in the wetland. Once they get done with the free oxygen, then they start trying to get the oxygen from somewhere else. There are elements around, so they start to get the oxygen the uh, from the iron compounds, magnesium, sulfur. Right. By the time you get to sulfur, it smells because calcium sulfate, when you take the oxygen, is still sulfate doesn't smell. That's one of the beginning processes. But eventually, you get to the sulfur when the microbes are they taking the sulfur out and reducing it and converting it to sulfide, and at that point it smells. So that's what the reason why in an extended process, which is an extended process in a wetland, eventually you get the sulfur, I'm being confused in here, the sulfides being produced. Therefore, it'll smell. And I think I already told you that in many places around the world, there's sulfide all over the dumps when you dump the water, I mean the sewage into the river. So what is methanogenesis? Methanogenesis is the last process in the degradation of organic matter. Because what happens is the bugs are eating all the furniture. By the time the furniture is gone, they have no other choice that start eating the building. And the building is CHO. That's a building. So try to get the O out of the CH. It's like we were trying to get the oxygen out of the bricks. You get the oxygen and then you left with the rest, which is CH. And CH is methane. So that's how there's a process of methanogenesis. They say, the scientists that know this, that methane is a much stronger producer of global warming than carbon dioxide. I think the number is 5 or 6. Of course, there's not a whole lot of methane because industry somehow we use methane, but not a whole lot. So it's overwhelmed by the carbon dioxide burned by transportation. Transportation is the culprit here. So methanogenesis is the creation of methane. It could be done naturally or artificially. And hopefully there are not that many places out there. There are some, but not too many. So that's methanogenesis. And it happens when the bugs, it could be artificial and natural, but I'm talking about the natural process. When the bugs, the microbia the microbes rather, that operate in the substrata decide to go after the building, after the matrix. And they do it. Eventually they do it. It takes time, but they do it. It's been argued that if you don't control a wetland, this thing could happen, and it could be adversely affect. It could adversely affect global warming, and that is true. And there's people around the world trying to measure the methanogenesis or the genesis of methane in the wetlands. So this is something that needs to be studied more. And finally, at the end, now we're going to getting 637. Explain why it is difficult to control floods with flood walls. I had an example in a movie that I showed you. What happened in the Ohio River during the flood of May 2011, and what is the current strategy to cope with the problem? Okay, long story made short. I went over there after they breached the levee into the reservoir that was supposed to hold the flood. And they did very successfully. And that was in the May 2011. And I was lucky to meet the people that were doing the cleanup. And they showed me a group of these. They actually said that they were 22 or 24 of these locations where the water coming from the river was going under the wall and going locally into the vicinity and appearing bubbling on the surface. Which immediately I realized that, boy, this really is a complex situation. Because if you didn't have the wall, you wouldn't have the bubbling. And if you had the wall, then you wouldn't have the flooding. So we traded the flooding for the bubbling. In other words, the flooding went out and the bubbling came in, which goes on to prove what I have said repeatedly. You can't do something good without creating something bad. That's called environmental impact, which is part of our hydrology study. So that's happened. It happened. Why did it happen there and not in many other places? Because the bubbling comes up with depends on the soil and also depends on the gradient. The gradient's got to be large enough. In this case, there were about 20 feet of gradient, large gradient. The river has been raised 20 feet in this level within the walls, concrete walls. So that was creating the bubbling and the boiling, actually. The word is boiling, the boiling of sand. And they were afraid, of course, that if it continues like that, you could create a hole under the wall, and out of control, it would probably destroy the wall. It's hard to believe, but anyway, we don't want a hole under the wall because the water will go through the hole, and then you will defeat the purpose of the wall, right? So that's exactly what was happening over there. There was July, no, that was July, May 17, 2011. I was talking to the Army Corps people, technical people, field people. They were telling me what was going on. And the interesting thing about it was that they told me, I don't remember the names now, but they told me that they were controlling a boil that, in their experience, was the largest ever seen in the US. I don't remember the numbers now, but I think 2 feet, the center of the bowl was 2 feet. And then the ball itself, they would ring the ball, and it was like a 24, 30 feet ring, which is a very large, because I saw many of them. Most of them were 2, 5, 4 feet, not 24. But he did wanted me to see that because that's important for my illustration. I submit that to see that again, you got to be lucky. First of all, it's got to flood. Second, it's got to flood extensively. Third, you got to be there. And fourth, you got to be with the people that are actually showing it to you. That may not happen in 100 years. And why did I say that? Because the New Madrid floodway, Birds Point, New Madrid. Birds Point is the upstream, and New Madrid is the downstream. Had been built in the 1930s and had not been operated to the 2011. It's a safety valve. It was a safety valve so that you wouldn't flood Nashville, which is downstream the Mississippi. So they built it because all flood control is always insurance. You build it in the case it happens, but you're very well aware that it may not happen. It may not happen in your lifetime. And I'm sure that the people that built the New Madrid floodway died. They were building this in 37. They would have retired in 60. They would have died at 80. And now in the year 2011, we had an occasion where we could test the wall and or test the wall and test Birds Point New Madrid floodway. The floodway worked well, but they were not thinking that the flood wall was not going to work well. I'm not saying it's a surprise, but they were not expecting that kind of damage because they hadn't realized the extent of the gradient. And that's one thing that we have to talk about here as we end this this presentation. Water is very well known by hydrologic engineers. The mechanical properties of the soil are well known by geotech engineers. But in the middle, there's a vacuum in there. In other words, the hydraulic engineers don't do the soil very well, and the soil engineers don't do the water. And that's right there where the boil is. It comes in that area. So there's relatively scant knowledge on the issue of how did you get a boil, where is it generated. We know, of course, that it is the gradient. It's high gradient creates a boil. That's true. But how to control it, how to study, how to analyze it, I submit that that is not a very well-known field even to this day. What the Army Corps was doing, they were just running around for the couple of weeks. Running around, I mean, they were going there inspecting the local situation, and if they found a boil, they were trying to ring it and so forth. And the question that I have in my mind is, how come some boils were small and some was big? And the answer is, depends on the soil. It depends on the soil. In the big boil, it was probably the soil was looser, it was more silty and so forth. While in the other places, it was stronger. So it was able to resist on its own the process of growing the boil. I saw many of these rings. The gentleman who was helping out, he said that they were identifying a whole lot of rings, and they were ringing about 20 of them, 20, 24. I saw rings 5-foot diameter, maybe 10-foot diameter, but the largest one was a 24 diameter. So I was pleased that I was able to have that experience. We recorded that with a video, as we normally do, and that was the end of that experience. So at that point, with that point made, I am going to stop in here. I can't believe that I'm 1 minute short.